Today let's review the frictional resistance in fluids flow. If you remember, the Reynolds number is given by rho v d by mu, which is the inertial, the force that drives the flow, divided by the viscous force, which is the internal resistance to the fluid flow. When it is 2100 or less, the flow profile is parabolic, and the ratio of the maximum velocity, which is at the center, this is at the center, to the average velocity, that will be determined by Q, volumetric flow rate by area, which is meter cube per second divided by meter square, which is meter per second, is half. In other words, the maximum velocity is 2 times the average velocity. In case of the turbulent flow, the difference is less. Typically, if this is the pipe, in a turbulent flow, the profile is like this. This is the maximum velocity, and the average velocity is here. So the ratio is pretty close to 1. It's 0.82, which is greater than 4,000. Okay. If it is transitional, okay, use maximum equal to twice the average. Consider like a laminar flow. Okay. If it is a transitional flow, consider it as a laminar flow. If it is a turbulent flow, use this condition. So the reason we are all studying this is because we want to evaluate what is the frictional resistance offered by a fluid during a pipe flow. So when a fluid flows due to the friction, there is a pressure drop delta P. The delta P pressure drop is proportional to, it is a function of Reynolds number, right? And a pipe diameter, the velocity, and also there is a frictional factor F. Okay, that frictional factor F, in case of the laminar flow, it is the Fanning's friction factor. It's given by 16 by Reynolds number for the laminar flow. The key thing to note down is this is a Fanning frictional factor. In civil and mechanical engineering, typically we use a Darcy's friction factor, which is FD, which is 64 by Reynolds number. Okay. So you need to clearly think through which one is used here. In chemical engineering and food science and food engineering literature, the Fanning friction factor is used, and that's what will be used in this textbook. So if you would have taken a fluids class, you might have studied Darcy's friction factor, which is 64 by Reynolds number. Overall, in the equation, that factor 4 gets multiplied, so it all gives you the final answer, but you need to be aware of these difference between the Fanning friction factor and the Darcy's friction factor. In case of the turbulent flow, it's a much more complex equation. The F is a proportion to the roughness factor. What that means is, in laminar flow, the surface roughness of the pipe doesn't matter. Whether it is a glass smooth pipe or a cast iron pipe or a commercial steel pipe or a plastic pipe, PVC pipe, it doesn't matter. The frictional coefficient F is 16 by Reynolds number. Whereas in case of a turbulent flow, the surface roughness factor of the pipe affects. That psi is a value given in the textbook in a tabular form. So D is the diameter. It still depends on the Reynolds number too. But more commonly we use what is called as a Moody's chart. So here is a Moody's chart. The Reynolds number is on the x-axis. If nothing is given, you can assume it as a smooth pipe or like a commercial steel pipe. So if the Reynolds number is, let's say 200,000, you go over here and then you come back. And this is the value of F for that factor. If it is a different frictional factor, you are going to move it. You can see that in the laminar flow, it is 16 divided by the Reynolds number. That's the formula we use. So once you know the fanning factor, you can measure the pressure drop delta P, which is equal to 2 times F, L over D, U bar square divided by rho. Okay. So when a fluid is flowing through the pipe, due to the friction, there is a pressure drop. And which is given by, which is proportional to the F, which is what we determined using Moody's chart or 16 by Reynolds number for the laminar flow. The higher the length of the pipe, higher the pressure drop. Larger the diameter of the pipe, smaller the pressure drop, right? Higher the velocity, higher the pressure drop. It's proportional to the square of the velocity divided by the density of the fluid. Okay. So the roughness coefficient psi is in millimeter, is given in the textbook. If nothing is given, I would recommend a safe assumption is a commercial steel. So you can use psi is equal to 0.046. State the assumptions clearly in the exams, okay? That basically concludes this talk.